Hello. So my company name is Hot Neuron. We do not do anything with neural networks. We just like to keep everyone confused. We do have a software product called Clustify, which does clustering and supervised machine learning, and I wrote it, so that's where I get my experience from. I'm also writing a book on supervised machine learning applied in the context of e-discovery, which is something I'm going to talk about a little bit. You can find some draft chapters at predictivecodingbook.com. Finally, I'll point out that I have a PhD in theoretical physics, which really doesn't matter at all, except that there will be equations on my slides, so you've been warned. So I'm going to talk to you about how we measure information retrieval performance. I'm going to be addressing issues totally separate from what Larry talked about. So the basics here, precision recall curve. Here we're highlighting, well, these dots are representing individual documents. Normally you'd have a ton of documents, but I want just a few so you can see what's going on. Orange means the document's relevant, blue means it's not relevant. So some systems, like supervised machine learning systems, can rank your documents based on how likely it is that they're going to be relevant. So they try to get the ones with the highest probability at the top of the stack. And you can pick any point in that sorted list to be your cutoff point to define documents above that point is predicted to be relevant, below that point is predicted to be non-relevant, and you can compute your precision and recall. So recall is the percentage of relevant documents that the system managed to find, and precision is the percentage of documents that it predicted that are relevant that really are relevant. And by picking each possible cutoff point within that sorted list, you can sketch out a curve. Precision recall curve off to the right is typically downward sloping because the further down the list you go, the more you're picking through the garbage that the system is not very optimistic about. Now, what part of this curve you care about depends on the context of what you're trying to do. If you're trying to find websites about skydiving on Google, well, there's a few million results that come back, but you're only going to look at the first few pages worth. So you're looking at very low recall, and you want high precision there. You don't want any junk coming back. In my industry, which is e-discovery, we care about very high recall. So what e-discovery is when somebody files a lawsuit, they can go to the court and they can say, we want the other party to turn over documents meeting certain criteria so we can dig through it and look for evidence that they did something bad. If you are the producing party that's turning over those documents and you don't do an adequate job of turning them over, you can be sanctioned by the court, which could mean losing a lot of money, losing the lawsuit. So in that case, you need high recall, maybe 75%, maybe 95%, really depends on the value of the case. Now what you would like to have also is high precision. Typically you're going to have a lawyer take those documents that are predicted to be relevant, go through them one by one and review them and make sure they really are relevant so they're not turning over anything that they don't have to. And that's very expensive, costs at least $1 per document. And so you don't want to have them wasting time reviewing documents that are not relevant, so it means you want high precision. So let's look at some actual precision recall curves. This is a pretty difficult task here, difficult categorization task. The curves are not too impressive. But what we really want to know is how well one system is doing compared to the other. In this case, the orange system is beating the purple one across the board. Whatever level of recall you want to hit, it does it with better precision, fewer non-relevant documents mixed in. Now sometimes you're analyzing a system that doesn't give you the whole curve. It doesn't sort the documents. It just gives you a yes or no prediction for each document. Maybe a rules-based system might do that. And so now we try to compare two systems and all we have is a dot. So the orange system has higher recall but lower precision. So is it better or worse? It's kind of ambiguous. Well, 30-some years ago, people came up with this thing called the F1 score. There are various other measures that also combine recall and precision into a single value so that you can try to make a comparison between two different systems when you only have a single point. In this case, notice first of all that recall and precision are interchangeable. They're treated like they're equally important, even though they mean very different things, like I told you from that context of e-discovery. Also, the F1 score is going to be between the recall and the precision, and it's going to be closer to the smaller of the two. So if we apply that, now the vertical axis is the F1 score. It might be a little hard to tell from the slide, but it is saying that the purple system has a slightly higher F1 score than the orange. But we know that the orange one is better. They're across the board. So what happened? Something went wrong. So let's go back to the situation where we actually knew the full precision recall curve and try to figure out what's going on. So these curves always wind up being hump-shaped. That's because on the left side of the graph, recall is small, so F1 is forced to be small. On the right side of the graph, precision is small, and so F1 is also forced to be small over there. So you're going to have some maximum somewhere in between. So we happen to take our cutoff point in that sorted list of documents for the purple system at the optimal point where it got the highest F1 score that it could. And for the orange system, we pushed the recall higher than F1 would like us to, and so we got a poor F1 score. So the F1 score here is not merely measuring how well the system is performing, it's also measuring how smart we were about picking that cutoff point in that sorted list. In fact, for the purple system, it's telling us we should cut off at 42% recall and just stop at that point, because going through the list deeper and finding more documents is going to bring in too many non-relevant documents. It's not worthwhile. But that's the F1 score sort of forcing its opinion of the world on us when it has no business doing so. If we're in litigation, we can't go to the court and say, well, we're only turning over 42% of the relevant documents because the F1 score is maximized there. So F1 is really not a good measurement for a lot of things. So another way of looking at this problem is to look at the contours of constant F1 score. So the contours in the upper right corner are high F1 scores, and towards the lower left you have the lower values. We see that the typical precision recall curves are going to cut across a lot of contours, meaning that the F1 score is going to vary a lot depending on where in that sorted list you pick your cutoff point. So in the purple system, if we pick the cutoff point to be exactly where it's optimal, that gray region shows you all the spots where another system could be doing better, but if we measured the F1 score for the other system in that spot, we would get the wrong conclusion about which one works better. And you see that gray region is pretty big, so there's a lot of territory there to draw the wrong conclusion about which system is working best. And if we look at the orange system, you see that by design, I picked the point to be in that gray region, and that's why it lost, even though it's a better system. So to avoid this kind of problem, what we really want is a quality measure that is going to have contours shaped like precision recall curves are normally shaped. That way your curves won't cut across a lot of contours, and thus the measure is not going to vary a lot depending on where you pick your cutoff point in that list. And so this is just showing our two precision recall curves, again, superimposed on those contours, and you see that they're pretty well separated. So this graph is just showing those 2 points and the contours that go through them. And we see that the contour that goes through the orange point is the higher contour, and therefore it is saying that this is the better system, and that is what we want it to say, so that's a good thing. But then we need to put a number on it. How much better is it? Is it twice as good, 3 times as good, or only 10% better? We need a number, and we want it to be a number that actually means something to us. So this brings me back to what I sort of mentioned at the beginning, which is if we're going to have a lawyer review these documents that are scoring well, it's going to cost us a lot of money, and we want to make sure that we're spending as little money as possible. So little n here is the number of documents from the top of the stack that you're going to have to review in order to reach recall R, which we're going to choose. Rho is the prevalence, meaning the percentage of the document population that is relevant. Big N is the total number of documents in the population. R is the recall we want to hit. And then P is going to be the precision at that level of recall that we want to hit. So the numerator is just the total number of relevant documents we're going to find, and that's all going to be stuff we're going to pick. And then the denominator is really our performance measure, the precision. So if the precision for one system is twice as big, that means we're going to review half as many documents, so half as much money wasted being sent off to those horrible lawyers. Wait, there are none of them here, right? None of my clients. So to quantify this, what we can do is we can take those curves that pass through our 2 data points, and we can slide down to the curve to a particular level of recall. In this case, I've chosen 75% recall. You see the vertical dotted line there. And we can just evaluate the precision at that point. And then we realize that what we're really doing when we're putting this number on our performance is we are extrapolating our precision from one level of recall to another. We're doing that extrapolation by sliding down this model curve, this contour line that we've constructed. Normally when you do extrapolation, you say, well, if I have 2 data points, I can draw a straight line. If I have 3 data points, I can draw a parabola. Here we have 1 data point. And so to get some real structure and meaning out of it, we have to impose this model, this structure that I've come up with for these contours. And when we do that, we find that this measure as a function of where you're picking that cutoff in that sorted list is a lot flatter than something like the F1 score. It's not going to be perfectly flat, and you could argue that in cases where it's not perfectly flat, it's showing you that the performance of your categorization tool has areas where it's better or worse than expected compared to this model that I constructed. So here's the math part. So how do we construct these curves? So the first thing that's important to realize is that we have this sort of list. You can pick any little slice of that list of documents and say, what's the probability of the document in that region being relevant, right? And we want that number to be between 0 and 1, right, because it's a probability. And that's going to relate back to the precision, which is going to be number of documents from the top down to that point. So we can't just write down an arbitrary precision recall curve out of the blue and have it necessarily work, because it might imply the probability is bigger than 1 or less than -1. So what we're going to do instead is we're going to model the probability and then compute the precision recall curve from that probability model. So the probability in this equation is little p, precision is big P, recall is big R. So we have this differential equation. So I'm taking the continuum limit where I'm assuming that I have basically an infinite number of documents so that I can do calculus instead of finite difference stuff. And the next line in the middle there shows that that differential equation is solved by doing an integral. And we have a boundary condition down at the bottom. Now when I actually do my model, I am going to replace big P with big X and little p with little x, just to keep in mind that I am moving from the real world precision recall curves to my model precision recall curves. And to do that, I need to actually look at some data to figure out what a nice looking model should look like. So I have some sample precision recall curves. I actually used more than what you're seeing here. You can find them in the research paper that's referenced in the last slide. I looked at 2 different data sets, total of 9 categorization tasks spanning several orders of magnitude different prevalence. So we do finite differencing to get the probability curves from the precision recall curves. So the finite differencing is going to make it look a little bit noisy, but that's okay. One thing that's worth noting, if you look at these curves, over towards the right-hand side, everything kind of looks like a parabola where r is close to 1. So we can think that the answer is going to look like something like 1 minus r squared plus a constant. But we also have to keep in mind that the probability has to stay less than 1. So as we move to the left, we can't just let this parabola go shooting off to infinity. So to do that, our model for our probability, which is little x on the top line there, we see the 1 minus r squared in the numerator. We repeat the 1 minus r squared in the denominator so that as long as that extra part, the c0 plus c1r plus c2r squared is positive, guarantees our probability will be between 0 and 1. I'm not going to get into the details of how you figure out what C0, C1, and C2 should be. There's a little eyeballing it and stuff like that, and then there's a normalization condition that goes into it. And then we wind up with the second line there, which is a really beautiful equation that only its creator could love. And then when we do that integral that was back on the previous slide, we wind up with our equation for big X in the bottom. On the bottom line. Now, I actually wrote the equation for 1 over x for typesetting purposes, so I could wrap that line around. So what we have here is we have a relationship between our precision, which is going to be big X, recall, prevalence, and then this parameter beta. So when we get our actual data point, our precision recall value, we have to figure out what value of beta will give the right value of precision out of this equation. And then we can plug in any value of recall we want to get that curve, that model curve for a precision recall curve. So it's a little ugly, but the results are nice. So if we look at how it fits the probability curves, we get these things. Now keep in mind, these curves are arising from looking at one single precision recall point for each of these. And so you have that nice smooth model curve that really has the right shape and structure to fit that rather complicated thing, even though we only have that one piece of input going into it. And here are the precision recall curves. So the dots show where I fixed the model to be equal to the actual data. And then as we go away from that point, which I chose to be 75% recall, you can see that the models are still pretty close to the actual real curve. So I would argue it's a pretty sane looking model. It's well behaved. There are a few little limitations about situations where the math won't work out, but they should really not be much of an issue in practice. So in summary, sometimes the recall level we want to reach is going to be dictated by things outside of simple precision and recall, like a court telling us we need to reach a certain level of recall, which might be influenced by the value of a case. So we want a performance measure that is not going to force us to aim for some arbitrary level of recall that's really not connected to that. So that's what I tried to come up with here. Again, this is an extrapolation scheme. So if we are extrapolating to a certain level of recall, that is pretty close to the value we measured, this should be a good extrapolation. And we're extrapolating from just one point. All this structure is coming in from fairly simple assumptions about what a sensible model would look like. And as I mentioned before, we're getting a performance measure out. Unlike F1, we're getting something out that is like a precision value, which means it relates to something that really means something to us in the real world. It's going to be related to the amount of money we would spend reviewing those top scoring documents. And finally, there's the full research paper, which is really hard to read, but if you download the actual slide itself, you can just click on it and review the whole research paper.